state and prove the fundamental theorem of arithmetic. Now, every natural number is greater than 1 can be expressed as a product of the prime in and only one way. Let n be the natural number greater than 1, since we know that every natural number other than 1 admits a prime factor. Therefore, n has the prime factor, say p1. p1 divides n. There exists an integer n1 such that n is equal to n1 p1, where n is greater than n1. If n1 is 1, then n is equal to p1, that is n is a prime p1. Now if n1 is greater than 1, then n1 has a prime factor p2, because every natural number other than 1 admits of a prime factor. So there exists a positive integer n2 such that n1 is equal to p2 n2, where n1 is greater than n2. Putting the value of n1 in 1, we get n is equal to p1 p2 n2, where n is greater than n1 n1 is greater than n2, so on. This is equation 2. So n2 is equal to 1, then n is equal to p1 p2. N is a either product of the prime p1 and p2. If n2 is, we continue this process, but this process must terminate after a finite number of steps. Since n is a finite, so n is greater than n1, n is greater than n2, and greater than so on. So therefore there exists prime p1 p2 and pr such that n is equal to p1 p2 so on pr. This is equation 3. Now uniqueness, let if possible n is equal to q1 q2 and q so on qs, with that is equation 4, be a second prime factor of n as a product of, from 3 and 4 we have p1 p2 and pr is equal to q1 q2 qs so on qs, which is equation 5. Now equation 5 shows that the prime p1 is a factor of the product of q1 q2 and qs. Therefore p1 must divide at least one of the p, say q1, but q1 is a prime, so either p1 is equal to 1 or p1 is equal to q1, but p1 is equal to 1 is not possible because p1 is a prime greater than 1, so p1 is equal to q1. Therefore equation 5 becomes p1 p2 pr is equal to p1 q2 q3 qs, and that is equal to p2 p3 so on pr, and q2 equal to q2 q3 so on qs. That is equation 6. As therefore p2 must be x equal to sum of the any other prime q2 q3 and qs. Without any loss of generality, we have p2 is equal to q2. Therefore equation 6 become p2 p3 pr is equal to p2 p q3 so on qs, cancelling p2 and p2 from both sides. So we have p3 p4 so on pr, q3 is equal to q3 q4 so on qs. Similarly we have p3 is equal to q3 and p4 is equal to q4 and so on. Finally we have to prove that r is equal to s. If possible, let r is greater than s. Therefore the equation 5 can be written as p1 p2 ps plus 1 p so on pr is equal to q1 plus q2 and so on qs. Putting the value of q1 is equal to p1, q2 is equal to p2 and qs is equal to ps. We have p1 p2 ps so on ps plus 1 so on pr is equal to p1 p2 and so on ps. Dividing both sides by p1 p2 and ps, we get ps plus 1 so on pr is equal to 1. But this is not possible because each of the factors of left hand side being prime greater than 1, so r is less than r is greater than not greater than s, and similarly r is not less than s. Hence the two of the factors factorization of n, namely p1 p2 pr and q1 q2 qr are identical.